Vector Calculus, Mathematical Preliminaries. In this short video, we're just going to review phasors, some Phasor Arithmetic, and then also introduce scalars and vectors and discuss some potentially misleading things about their notation. Anytime we have a time harmonic function, that is a function that follows a sine or a cosine, we can write it as an amplitude term times a cosine, and the argument of the cosine has a frequency term omega, and of course a time term, and then a phase or angle term. Now, we can do all of our math with this cosine, but it turns out our math becomes easier if we use this thing that we call phasor notation. And we can use this anytime we have a function that is a sine or a cosine. To get to what a phasor is and how we write it, recall Euler's identity. Euler's identity relates our sines and cosines to a complex exponential. And so we see that the complex exponential of the angle argument theta equals cosine of theta plus j times sine of theta. That means our time function y of t is the real part of our amplitude times this complex exponential with an argument of j times omega t plus theta. Because if we plug this j times omega t plus theta into Euler's identity, and then of course just take the real part of that, we get our cosine back, cosine of omega t plus theta. At this point, we will factor out the e to the j omega t term. And in the next slide, we'll get rid of that. So we start with the equation we had on the previous slide, and I promised we would be getting rid of the e to the j omega t term. So let's go ahead and do that. The reason that we get rid of that is because in a linear system, frequency never changes. So if we're doing a long derivation, we'll just keep writing e to the j omega t and keep writing that, and it never changes. So in fact, we ask the question, why even write it then? So in fact, in phasor notation, almost always that e to the j omega t is just not written. And finally, to the lower right corner here, our term capital Y is our phasor. And we really just write the amplitude and the angle. The e to the j omega t technically should be there, but since it never changes, we just ignore it, and we say that it is implied. We no longer write it explicitly. So that's a phasor. So here's how we visualize a phasor. There's a lot going on here, so let's take a bit to think about this. First of all, the only thing that is real in that sense is this time function y. So y equals a times cosine omega t plus theta. So the blue line that we're showing to the upper right, that is the function. Everything else we're showing here is a mathematical abstraction, but it makes our math and analysis with time harmonic functions much easier. So in the lower part of this animation, this is where you see the actual phasor. And so we draw an arrow connecting from the origin to some point on the surface, and that point constantly rotates around this circle. The radius of that circle is a. So that is the amplitude of our sine wave. But this angle is constantly changing. That's the omega t term. That's time. Time is making this phasor spin around and around and around. The phase angle theta would simply just add an offset to that. So in a way, that's not conveyed in this diagram, just the time function. And so we can see that the time function is always the real part of that phasor, the horizontal projection of that vector. The vertical direction, sometimes people call that imaginary space. It's just stored there. It can affect our problems, but when we are interested in the end of what the actual value of the function is, it's always the real part of the phasor. We tend to write our phasors in one of two forms. Probably the most common is the polar form. This is where we write what we've been doing, where we write the amplitude and the angle. And most of the time you'll see it as an amplitude and then a complex exponential with angle theta. But sometimes you'll just see the amplitude, some kind of angle symbol, and then the angle. Both of those mean the same thing. So one does not mean something different than the other, and we don't need to get stressed out about that. They mean the same thing. We can also write that in rectangular form. So instead of having an amplitude and a phase, now we have a real and an imaginary part, alpha and beta. So we'll call that the rectangular form. And of course, we can convert back and forth. If we have the rectangular form, so we know alpha and beta, we can calculate the polar form. That amplitude A is simply calculated from alpha and beta using the Pythagorean theorem. It's the hypotenuse of the triangle where alpha and beta make two sides. The angle theta is simply the inverse tan of beta over alpha. If we have them in polar form, we can calculate the rectangular form. The real part, alpha, is just a times cosine of theta, and the imaginary part, beta, is just a times sine of theta. Now, when we're doing multiplication and division of phasors, we tend to prefer to work in the polar form. So if we're given the rectangular form, we'll have to calculate the polar form, do our math, and then if we need to, convert back to rectangular form. When we're doing addition and subtraction, we prefer to do that in the rectangular form. So if you're given the polar form, we'll convert to rectangular, do our math, and if we need to, convert back to polar. So we need to be practiced at going back and forth between rectangular and polar as we calculate equations that have both addition, subtraction, multiplication, and division. So let's talk about the Phasor arithmetic. So addition is done in the rectangular form. And we simply just add the real part of both, and we also just add the imaginary part of both and keep that being imaginary. And that's how we get the sum of two phasors. So it should be no surprise if we subtract two phasors. The real part is just the difference of the real part of the two phasors, and the imaginary part is just the difference of the imaginary part of those two phasors. Now we'll move on to multiplication. Now we do multiplication with the phasors in polar form. So we're working with amplitude and angle instead of real and imaginary part. So if we're multiplying two phasors, the magnitude of the phasor is just the product of the magnitude of the individual phasors. And interestingly, the angle of this phasor is the sum of the angles of the two phasors. So we don't multiply those angles. That's an easy mistake to make. We multiply the amplitudes, but we add the angles. For division, we divide the amplitudes and we subtract the angles. And it's very important to keep the order of your thetas straight. So we always take the angle of the first phasor and subtract the angle of the second phasor. And of course, the amplitudes we're just dividing. So as I mentioned before, for addition and subtraction, we'll do that with our phasors in rectangular form. And for multiplication and division, we do that with phasors in polar form. So we need to be very good at going back and forth. The last thing we'll talk about is scalar numbers versus vector numbers. And we really should be calling these scalar quantities and vector quantities. So what is a scalar quantity? It's a quantity where there's just a single number associated with it. And of course, when we go on to vectors, they'll include a direction. So scalar numbers, it does not make sense to associate a direction with it. It's just a single number. And so pi, for example, is a scalar number. There's no direction associated with that. Your weight, for example, might be 100 pounds. It doesn't make sense to have a direction associated with the weight of your body. Now we can talk about the force due to gravity, and suddenly that starts having directions, but that's no longer a scalar quantity. Vector quantities carry two pieces of information. They have a scalar number associated with them. That's the magnitude of the vector. But they also have a direction. And so the classic example of this is velocity. You're driving down the road at 60 miles per hour and you're traveling north. So you have both a speed and a direction. And of course, in this class, the electric fields are vector quantities. The magnetic fields are vector quantities. We'll talk about force. That is a vector quantity. Current density, that's a vector quantity. We have a lot of vector quantities because in electromagnetics, the fields push in particular directions. And so there's definitely this directionality associated with it. Let's talk about the notation. So vectors are usually drawn like what we have here. Sometimes there may or may not be a point at this side. I'm drawing that to saying this is the origin of the vector. And then we draw the vector with an arrow. And of course, the arrow is pointing in the direction that the vector is pointing. And in this case, we're talking about a vector that is parallel to the screen. I label it as paper because you may have this printed out on paper. Now, if that vector is in a third dimension and sticking out of the screen toward us, we would draw that as a circle with a dot in it. Think of it as the tip of an arrow and it's pointing straight at us. And so that analogy makes some sense too when the vector is pointing away from us but still perpendicular to the screen. We will draw that as a circle with a cross in it, just like you're looking at the back of an arrow where it has the feathers or the fins. And the last thing I'll point out, when we draw vectors this way, if you're new to vectors, this can be misleading because it seems to imply that even though we're talking about a vector at this point, that something's happening at a different position over here. And that's unfortunate that this way of representing vectors does that, because we're not talking about something happening over there. We are talking about something happening at this point here, and that's it. It's just that we have to draw a direction associated with it, so we're forced to have to draw something that just moves away from it. But we are not implying that anything is happening over here. This entire vector is talking about something happening at an infinitely small point right here. So think about that when you're looking at vector notation. Anytime you see a vector, we're talking about a function at a very specific point and not away from that point. So what can vectors convey? One thing they can convey is position. When they're conveying position, this is almost always done relative to the origin of your coordinate system. So we'll call the origin 0, 0, 0 for x, y, z. And so if we have a vector, it is pointing from the origin to the point that we're actually talking about. In this class, very often we'll use lowercase r with a little arrow over top of it, meaning vector position. We could also be talking about a vector distance. We'll be doing this a lot in electromagnetics. In this case, it doesn't really have an origin associated with it. It's just the distance between 2 points. And so we'll have to know what these 2 points are really to draw that vector. It could also indicate some kind of disturbance. An electric field, for example. The electric field can be different everywhere. The electric field looks a bit like a cloud or a fog. It's sort of smooth like that. But at each point, there's also a direction associated with it. If we could place a charge in the middle of an electric field, it would get pushed in a very specific direction. So in this case, we're using vectors to describe some kind of disturbance which has a push in a particular direction and also a strength to that push. So if we think of these three things, vectors, while they're all vectors and mathematically just looking at them, we really can't say anything else about them, they really can sort of convey different things at different times. But these are the big three in this class: position, distance, and disturbance. So if we have a vector, we remember that a vector conveys two different things: some kind of strength and also some kind of direction. Sometimes we'd like to get rid of that information or get other information from it. A big one is, what is the magnitude of that vector? And so we use a generalization to the Pythagorean theorem to calculate that. The magnitude of your vector A is the square root of the components of that vector squared, the sum of those. So the x component square plus the y component square plus the z component square, the square root of all that is our vector magnitude. When we calculate the vector magnitude, we've dropped the direction associated with that, so we will no longer have that information. Another thing, we might just be interested in the direction and not the magnitude, in which case we'll take a vector and divide by its magnitude, which we now know how to calculate. So we get another vector, but the magnitude of that vector is 1. And if it had any units before this, those units are now gone because vector A has those units and also its magnitude has those same units. So when we divide by its magnitude, the units vanish, and so the magnitude of a unit vector is completely gone. It only conveys direction. And we will do this a lot of times when we only care about the direction of a vector and we don't want to let the magnitude of that vector pollute our calculations.